put a couple of... Another some of my sample tests I can ask about some of the key historical dates in satellite engineering. The first one I like to put up is 1945. This is long before we put a spacecraft or anything into outer space. But this was an important article by the science fiction writer Arthur C. Clarke. This is actually a technical article. He wrote an article called Extraterrestrial Relays in Wireless World magazine, a periodical. And his idea was radical at the time. He says, you know, if we could put a radio in space, you could send a signal up to the radio, and it would bounce back to another part of the Earth. And that part could be beyond the horizon. And you would still get the signal. That was actually a pretty radical idea in terms of radio communications back then. The only way to get signals beyond the horizon, from a communications standpoint at this time, you could use the telegraph, or you could bounce a signal off the ionosphere. Anything like 1 megahertz or less bounces off the ionosphere because the charged particles are dense enough for those low frequencies to act like a perfect electric conductor. And it bounces the signal to another part of the Earth. Obviously, you don't get that much bandwidth. And of course, there's only a certain amount of spectrum available. If the entire Earth has to reuse that same spectrum for its bounces, then it becomes a very cluttered radio channel indeed. And of course, the telegraph isn't a very convenient way to send information either. In fact, we're still, believe it or not, you believe me, we're still basically doing this back in 1945. It wasn't until the 50s that we had the transistor. That's when they laid the cable. And it took until the 50s because there was really no way to regenerate the analog signal reliably under the sea. You can even do it with tubes, right? You can't exactly change the tubes out if they burn out at the bottom of the ocean. So, you know, that sort of options were very limited back then. So this was a radical technology for sending signals beyond the horizon. And we use a lot of satellites for a lot of different things nowadays as well. We use them for surveying, we use them for geolocation, navigation systems. But this was a fascinating application that began the race for space. There's a big prospect that the U.S. is doing a lot of research at this time to use things like communications. So we wanted to spy on the Russians, right? So how do we do that? Things in the right spot. 1967? Anyway. Almost 60 years ago. First time we were all and that forced America to get its act together, and next year we launched Explorer 1. And the space race was on. That's the first U.S. satellite. And then later that year there was another satellite called SCORE. The first one was Explorer 1. SCORE was the first one to actually transmit a voice broadcast, transmitted President Eisenhower's State of the Union address at that time. And you were all lower on this satellite, what that means in a second. And then in 1962, Bell Labs launched the first commercial communications satellite. Telestar 1 and 2, actually 2 satellites. And this became sort of the template for the next several decades of a classic architecture, the classic analog bent pipe architecture in satellite communications. It had an uplink of 6.389 gigahertz and a downlink of 4.169 gigahertz. And it's full of constant batteries and had a single transponder on it. It had the multiple ones that would come later. So we're really the first commercial launch of space. And then in 1980, we had some of the first GPS satellites go up. Satellite system that they had been working on in the late 70s. And this is one of the big innovations in navigation. And in fact, we're so pervasive that we use it to this day still and take it for granted. It's on every phone you've got. It's in bank ATMs. It's in all sorts of crazy things that want to do time and space positioning very precisely. And usually, after we've covered everything in this class, we start off with astrodynamics. You got to understand where your radios are going to be in order to communicate with them, what the limitations are. Then we move into antennas and propagation, and figure out how to send signals to and from a device. And we get into telecommunications, and then at the end of the course, I usually spend time working through how GPS works. The last week is geolocation using GPS. There's such an elegant synthesis of all the pieces that we learned up until that point. So GPS launches at 1980. And then in 2000, you had a lot of low Earth orbit, LEO, low Earth orbit satellite systems launched, like Iridium, Globalstar, Orbcom is another one. These are constellations of 60, 70, 80 low Earth orbit satellites that are providing global coverage to anyone with a personal handheld handset. And I've got some more data I'll cut it off here, but now some of the recent things that have been going on in space, we've got the privatization of space. Private companies actually handling launches instead of governments. That's actually a big deal. The cost of launches coming down. Some other interesting historical things are happening. Actually, one of the things I've gotten a lot of phone calls about recently, recruiters from Google and some other companies that want to put CubeSats into space. A CubeSat is a small satellite, has these standard dimensions that go up in payloads. It becomes a very popular platform for launching little satellite projects. Somebody wants to launch CubeSats into outer space and take a picture, do surveying, take a picture of the Earth, every square inch of it, every day. So you have this massive database of what the Earth looks like every day. Kind of creepy, but interesting. Cool communication project, cool satellite project. So I'm even wondering, I'm getting so many recruiting calls, I'm wondering if maybe that should be our project, to design that system for them, for free. Okay. Now, this is the part where you got to do some math. I'm going to take you back to your freshman or sophomore physics class, and we're going to build our understanding of orbital mechanics from the ground up. We're going to start with Newton's law of gravitation and good old F equals ma. We're going to first start with the simple stuff. I'll derive the kinematic equations. We'll look at the special case of circular orbits, and once we're comfortable with that, we'll move to what a elliptical orbit is, which is the general case of a stable orbit around another body. And we'll do that by introducing Kepler's 3 laws. And basically, we'll be building the terminology that we need to talk about all the orbital mechanics that you need as an electrical engineer to talk about a satellite in orbit. So, let's start at the beginning. Okay. In Newtonian gravitation, I've got two masses always. There's mass 1 and mass 2. And they're separated by a distance r. R is the separation distance. And if these have masses, they are going to mutually attract one another. There's going to be a force on object 1 due to mass number 2, and a force on 2 due to mass number 1. And they're going to be equal and opposite. Equal in magnitude, opposite in the direction. So magnitude is F2, F21 is equal to F12. And the formula for this, if you remember from physics, is G M1, M2, the product of the masses, times this magic gravitational constant, which is 6.672 times 10 to the negative 11th. That's units of Newton meter squared per kilogram squared. And then divided by r squared, which is a 1 over r squared law, like some of the other field equations in physics. So, that's how we start. Now, Newton also came up with some pretty sharp things to say about the motion of objects. So Newton's law of motion, one of the bedrock concepts in physics, F equals ma. Force is equal to a mass times an acceleration. My high school, you knew you're at bedrock physics. My high school English teacher put this on the board and called it Newtonian mechanics. And one of the students asked me, raised a hand. He said, well, can you explain what this means again? And the professor kind of looked at it and he said, well, you see, F equals ma. I'm not sure you can really give a better description of it, right? This is how it works. This is the world. And so it kind of cracked up the class a little bit. But F equals ma. And the interesting thing about this is that even though we try to present these as two completely different formulations, Newton's law of gravitation and Newton's law of motion, it's interesting that they use the exact same masses in one another, and then if you equate them, one of the masses drops out, the mass of the moving object. And so, even at this point in time, this is actually one of the hints of the idea of general relativity. It just so happens that these masses are the same, and they always drop out when you put them together. And so that the object is left with just this intrinsic property of space and its own mass, or the mass of the object nearby, that is influencing its motion. So let's go ahead and work through that quick exercise. If every force makes an acceleration, then let's say I'm going to study the movement of mass 1. system that I've drawn over there. If that's true, then m1 times a1, acceleration of 1 times mass of 1, should be equal to g m1, m2, r squared. Of course, the masses cancel, and the acceleration of body 1 is only due to the presence of the mass of the object number 2. And it's a profoundly simple result. Now, we're engineers, so we have to do this rigorously. I'm throwing everything as scalars at this point. So to really understand orbital mechanics, we're going to have to move into a vector representation. And so here's the convention that we're going to use to talk about orbits in this class. We're going to have a origin. And it is more convenient at this point to work in the cylindrical coordinate system instead of the Cartesian coordinate system. So instead of describing an orbit in terms of x and y, I'm going to use r and theta. And that is actually the physics and mathematics convention, not the electrical engineering convention, because most of this stuff comes out of physics and mathematics books. Electrical engineers haven't written that much about orbital mechanics. If we were doing the cylindrical coordinate system, it would be what? Rho and phi. That's how electromagnetics engineers talk about these things. So this is r, and the angle that you would make with what normally would be the x-axis in the Cartesian coordinate system, that's what I'm going to call theta. So those points in space, if I describe it as r and theta, that will describe in a two-dimensional space the trajectory of my orbit. R as a function of time and theta as a function of time. Okay. Now, everything that I'm going to draw on the board is going to be two-dimensional, without loss of generality, right? Because if I have a planet and I got a satellite orbiting around it, there is a plane that's going to contain the centroid of that planet and all the points on the orbits. I'm going to have to tilt the plane and do some crazy twisting with it, but there's always a plane that I can normalize the problem, and that greatly simplifies everything. The math of the analysis. In fact, when you do homework number 1, which I'll assign probably early next week, what you'll be doing is doing a 2D code, and then when you're finished tracing out the orbit, you're going to twist and tilt it up until it's inclined, and then actually do a sky track or a ground track of the orbit, the track that it makes along the Earth, and then the track that it makes across the sky, which is ultimately where a lot of this analysis is going. We're electrical engineers. We want to be able to point antennas to our satellites. How are we going to know where to point them if we don't understand our orbital mechanics? So that's one of the key questions that we want to ask at the end of this. So don't get too bogged down with the mathematics. There's light at the end of the tunnel. Okay, so my trajectory is a pair of coordinates r and theta, and they're going to change as a function of time. They're going to be time-varying functions. And then from here on out, I'll probably just drop the parentheses t, because we all know that they're going to change with respect to time. Now, mathematically speaking, not talking any physics now, just pure mathematics. If you pick up your old dynamics book from your freshman year or sophomore year, for those of you that even take dynamics anymore, in the back, there's all these formulas that tell you how to get velocity from a position vector in any arbitrary coordinate system and the acceleration. And I'm just going to give you what the back of the book says for the cylindrical coordinate system. Velocity vector in terms of r and theta is given by r dot, r hat, the unit vector that always points away from the origin, plus r theta dot, theta hat. That's an orthogonal unit vector, theta hat, that always points in the direction of increasing theta. The dots, of course, is the first derivative with respect to time. And you'll notice that we didn't just take r dot, stick it on the r, and theta dot, stick it on the theta. That's something that my undergrads make a mistake of whenever they're doing vector operations in my electromagnetics class. You get away with that kind of horseplay in Cartesian coordinate systems because x hat and y hat and z hat are fixed with respect to your point of observation. No matter where you go in life, in a Cartesian coordinate system, x, y, and z always point in the same direction. So they're constants. One of the double-edged sword about when you move into coordinate systems like the spherical coordinate system or the cylindrical coordinate system or whatever crazy coordinate system some mad PhD has invented to solve a problem and escape his PhD program. Those coordinate systems are formulated in a way to simplify some geometrical aspects, but they often complicate other aspects. They almost always complicate taking derivatives, because if I take the derivative of r on the r hat and theta here, these r's and thetas change depending on my points of observation. So I can't just take the derivative. It's not even dimensionally correct. Like theta dot is radians per second. I need something that has units of meters per second in order to be a bona fide velocity. And so that's why I got to multiply those two things. Acceleration is even uglier. If you want to take the next derivative with respect to space, and you look at the back of your dynamics textbook, it's just crazy expression. R double dot, second time derivative with respect to time, of r with respect to time, minus r theta dot squared, sticking on the r hat, and then finally, that's all with just the r hat. Then on the theta hat, you have this component, r theta double dot, second derivative of theta with respect to time, plus 2 r dot theta dot on the theta hat unit vector. Okay, so that's it. I don't think I made any boo-boos. Now, how do we it should be. Okay, so going back over here, let's make a more formal treatment. My acceleration vector is going to be equal to minus GMP over r squared, stick it on the r hat, plus 0 theta hat. How did I get this? Okay, first of all, we're gonna leave the textbook physics world and enter into satellite communications. What am I orbiting? Planets, usually. I just call this M sub p. That's going to be the mass of the second object. Now it's the mass of the planet that's exerting gravitational forces on the spacecraft. There's your Newtonian constant, r squared, minus, it always points towards the origin. We are going to place our planet at the origin. The center point of the planet is at the origin. Then I have an r and a theta that traces out a trajectory around there, and it has to follow this equation. So Newton's force always points inward, so I conveniently align myself with the cylindrical coordinate system. There are no tangential forces, so I'm going to assign that equal to 0. And this gives me a great way to solve the system now, because this is the mathematical definition of my acceleration vector. All I have to do is equate the r hat components and the theta hat components. So I have basically two coupled differential equations now to describe the motion of this system. We have r double dot minus theta dot squared equals minus GMP r squared. That's equation number 1. And then finally r theta double dot 2r dot theta dot. The sum of those is equal to 0. Any questions so far? So really, the first week or so of class is just solving that system right there. It's pretty simple. It's pretty simple. And then also describing how does real life deviate from this. Because real life is never this clean, unfortunately. I think orbital mechanics is about as clean as anything gets scientifically to solving a pristine differential equation system. But even there are some irregularities. Now we're going to start by solving this for the simplest possible system, okay? The simplest possible system, the circular orbit. The circular orbit. For circular orbits, we have one beautiful condition. R is equal to a constant. A satellite in a circular orbit always stays the exact same distance from the centroid of the planet. And with this really simplifying assumption, if we are to have a circular orbit, then we can derive some pretty simple conditions for what that orbit has to satisfy based on this dynamic set of equations. So, let's go ahead and take a look right here since we have them up. R dot, double dot. If R is a constant, every time you see R double dot and R single dot, you know those are 0, right? So those go away. And every place, not the whole thing, just that part. And every place that I see a little r, I can just make this into a constant. There we go. So now, I have some interesting formulas to describe the conditions that I have to have for satellites. First thing, there is no angular acceleration. P theta, which is the theta component of velocity, you'll see from the second equation that theta double dot is equal to 0. Divided through by r, theta double dot is equal to 0. So there's no acceleration. The angular sweep must always be constant for a circular orbit. We can get what that angular sweep is from the top equation. I divide through by r, take away the negative signs, and take the square root. That gives me r theta double dot. When I plug in that top equation for theta double dot, that gives me the square root GMP over r. One of the most valuable equations you'll learn in this class. Velocity of an orbiting spacecraft is equal to the square root of Newton's gravitational constant times the mass of the planet divided by the distance away from the planet. And so there's an inverse relationship. The farther you move the satellite away from the planet, the slower it travels to remain in a stable circular orbit. So it travels slower, and it has a longer diameter around